Welcome to today's lesson on the power of simple machines and mathematics to solve real-life problems. You might recall that simple machines make the physical work of lifting or moving objects easier by providing mechanical advantage. Mechanical advantage is simply a relationship where the force required to get the work done is less than that necessary to move the object directly, but will require the worker to spend more time or travel a greater distance. So, to begin this lesson, first we will take a look at the lifting problem that we will be solving. Then we will spend some time learning inductively about levers. Many times throughout the lesson you will be given opportunities to make observations and conjectures. If you are able to stop the video during those times, it will give you all the time you need to do your part in engaging in the learning and building of the knowledge for yourself. Please stop the video when you hear this combination of notes played on the piano. Now, let's take a look at the application problem that our understanding of levers will allow us to solve. There is a very large rock sitting at the base of a tree. You have a pole that is 10 feet long, the tree, and some rope. You weigh only 120 pounds and you need to lift the rock that weighs 360 pounds. Your task will be to draw a picture showing how to set up the lever so that the large rock can be lifted using only your body weight and the lever. An important aspect of this task will be to determine how far from both ends of the pole you will make the fulcrum or tipping point so that the longer side that you will pull on will be just long enough to give you that mechanical advantage to lift the rock. Spend a minute drawing what you think the lever setup will look like, and remember to label the distance that the fulcrum is from both ends on the pole. But first, before we move on to learning anything new, let's see if we can activate our prior knowledge by looking at a couple lever setups, making a few observations, and even asking a few questions to get our minds going as we begin to learn perhaps something new that you haven't learned before. Take a look at setup number 1. Make 2 observations, write 2 questions. For setup number 2, make 1 observation, write down 1 question. Let's begin the lesson. What observations can you make about the setup shown? Where would you place a mass on the right to make the lever balance? If you said hang a 10-gram mass from the 80 mark, you are correct. How far are the masses from the center? That's right. Each mass is 30 units from the center. What is causing this lever to be out of balance? Although the masses are hung both at 30 units from the center, the 20 grams on the left have a greater force than the 10 grams on the right. What additional questions do you have about the lever so far? What observations have you made so far about how the masses can be hung on the lever to achieve a balance? What do you notice about the distances and the masses? If such a setup is possible, draw a picture showing how to hang an unequal amount of mass on the left and on the right, and yet still achieve a balance. Would this arrangement of masses cause a balance? Develop an argument and defend it to your peers. No, this arrangement of masses would not cause a balance. Would moving the mass on the right out to 20 units from the center cause a balance? Again, discuss with your peers. No, This placement of the masses on the right would not cause a balance either. Would placing the mass at 30 units from the center cause a balance? Again, discuss with your peers. No, again, this arrangement will not work either. Would placing the mass on the right at 40 units from the center cause a balance? Again, discuss with your peers. Yes, this time the forces on the left and right are now balanced, causing the lever to be in balance. What do you notice about the distances and masses? What about the setup makes everything balance out? Again, what do you notice about the distances and masses? If your observations led you to believe that the relationship of the distances and masses would cause the lever to be in balance, you are correct. What is that relationship between the distances and masses? To answer this question, we will work a few more problems. Based on what you have learned so far, or just through informed guessing, what would be the value of the unknown mass on the left to cause the lever to be in balance? The answer, 50 grams. What is the value of the unknown mass on the right? The mass on the right would have to be 10 grams. What is the value of the unknown mass on the left? Notice the mass is hanging halfway between the 20 and 30 mark on the fulcrum. The mass on the left is 20 grams. For the next 3 problems, you will be given the value of both masses, but have to decide how far from the fulcrum to place the mass that is not currently hanging from the lever. Where would you place the mass to strike a balance in this example? You would need to place the 30-gram mass all the way at the end at 50 units from the fulcrum. In this example, where would you place the 30-gram mass on the left to strike a balance? This time, 40 units out from the fulcrum. Where would you place this 20-gram mass on the left to strike a balance? The 20-gram mass would have to be hung halfway between the 20 and 30, or 25 units out from the fulcrum. We have just spent a good deal of time using the inductive method to learn about levers. We have guessed or made conjectures, tested and refined in hopes of coming up with an idea of how levers work. Have you come up with a generalization about the requirements for the lever to achieve balance? Talk it over with your peers. Now I would like you to take what you have learned and write your conjecture in the form of an equation that relates one side of the lever with the other. The equation should include mass and distance on both sides. Good job, here it is. Mass 1 times distance 1 on one side equals mass 2 times distance 2 on the other side. That means that the product of the mass and the distance on one side of the lever or fulcrum must equal the product of the mass and distance on the other side of the fulcrum or lever. In all of our work up to this point, the lever was balanced such that the fulcrum was at the 50. But in most cases where you are looking for mechanical advantage, you would set the fulcrum at some point not at the center. Actually, the fulcrum would be closer to the heavier object than the opposite end where you're pushing. What is causing the lever to be out of balance in the case of this diagram shown here? Since the fulcrum has been moved to the left, causing more of the lever to be protruding to the right than to the left, there's more mass on that side, and therefore the lever tips down on that side. I believe we are now ready to address our application problem with a little more mathematical certainty. The application problem reads as follows. You have a pole that is 10 feet long, a large tree, and some rope. You weigh 120 pounds and you need to lift a rock that weighs 360 pounds. Draw a picture showing how to set up the lever so that the large rock can be lifted using your body weight. You've already drawn the picture. Now the question is, how far from the ends should the lever be hanging by the fulcrum such that we can actually lift the rock? I will now go through with you the steps to setting up the lever, and then once it is set up, we can address the important question of where to set the fulcrum so that we can actually have the desired mechanical advantage. The first step to making the lever is using the rope to make a loop around the branch that is above the rock just slightly to the right. The next step is to take the remaining rope and make a cradle around and slightly under the rock. The third step is to take the 10-foot post, slide it through the loop, and attach it on the left end to the cradle around the rock. The next step is to jump up, grab onto the force end of the lever, and then of course the rock will lift as you descend down to the ground. And now, getting to the ultimate answer, where should the rope looped around the tree branch or our fulcrum be attached to the pole? That is, what should distance 1 and distance 2 be on the 10-foot pole so that we get just enough mechanical advantage to lift the rock? Since neither distance 1 nor distance 2 was given to you, even though you have the equation of the product of the mass and distance on one side equals the product of the mass and distance on the other, you are going to have to use some guessing and checking. But, being as smart as you are, I am sure that you figured out that the distance 2 had to be 3 times the distance of distance 1. 3 plus 1 is 4, so dividing that 10-foot pole by 4, we get 2.5, which means that distance 1 should be 2.5 feet, and distance 2 should be 7.5. Thank you very much, and I hope you enjoyed this lesson.